In this video, we're going to look at APP in a little more detail. In the basic mono RGB demo, we simply loaded our light frames, our calibration frames, and then we went straight to the integration tab. We bypassed all the other steps, and we didn't talk in any detail about the fields like signal to noise ratio or full width half max, etc., that get populated for each of our light frames in our frame list as we apply each step. The only recommendation I made is that you adjust the slider for the percentage of light frames. This is fine to get started, but the problem with this approach is that the adjustment is arbitrary, and the same percentage is then applied to every filter. So you may inadvertently allow bad frames to be integrated, or vice versa, filter out perfectly good frames. In this video, I'll present a better approach. We'll go through each stage and have a look at the settings that I typically change. If I don't talk about a setting, then that's something I typically never adjust from the default. I won't talk about mosaics in this video, at least not in depth. Maybe I'll refer to it in some of the settings, but we'll have a dedicated video on mosaics at some stage in the future. So in this example, we're going to add hydrogen alpha data to our HaLRGB data of the triangle of galaxy. The HA data was collected on a different night with a refractor. The HaLRGB data was gathered using a reflector. I also gathered luminance and red data with the refractor, but we can't use that as we've got diffraction spikes with the reflector and we don't have diffraction spikes with the refractor. Given its HA data, we're going to remove the stars anyway to add it to the luminance and the red channel, so everything should work out fine. So if we go to the load frame, we want to enable multi-channel processing as we have data from multiple filters. We want to enable multi-session processing as we have data from multiple nights. We can enter our target as M33, and we can load up our light frames. Before we move on to the calibration tab, we can check our light frames in the frames list. So you can see here that the blue frames are assigned to session 1, the green to session 1, the HA to session 2, the luminance to session 1, and the lights to session 1. Always good to spot check. You can also see that the number of stars, star density, background dispersion, signal to noise ratio and noise, full width half max, and the quality score and the registration root mean square, these values are not as yet set. So these values will get populated as we progress through the various stages. So if we move on to calibration. So calibration is where we take all of our calibration frames and generate a master bias, if we have a bias, master darks, master flats, and bad pixel maps for hot and cold pixels. And then we assign those master calibration frames to our light frames. After the calibration process has run, we can look at our light frames and see how well the calibration has worked. This is something you may want to do, especially if, like me, you try and reuse your flats. At some stage, the flats will stop working effectively and it's time to regenerate them. Ditto if you find the flats are over or under correcting, then it may be time to regenerate your library of dark frames. Typically, I regenerate my darks every 6 to 12 months. For my lights, I regenerate if I change out anything or I rotate my imaging trim. Here, you want to leave all the defaults as automatic. APP has very good documentation embedded in the app via tooltips. In this example, you can see that the default automatic option selects median or average depending on the number of light frames. In this case, we have more than 20, so it will integrate using an average. So we leave all these settings at their default. Under cosmetic correction, if you have an older CCD that suffers from hot or cold columns, you may want to enable and tweak the values. If you have a relatively new CMOS sensor, then you can leave these turned off. The rest of the settings I leave at the default. We can then go and hit Create Masters and Assign to Lights. This will take a while, so I'll fast forward to the end. So that's finished. It took about 30 minutes or so. So if we have a look at the frame column in the frame list, you can see which calibration frames have been assigned to each light frame. You can see here for this top one that we have a master bias assigned, we have a master dark assigned, master flat assigned, and a bad pixel map. And the CA here stands for calibrated. If we load up one of the light frames, so we take this top one, and there's a drop-down box at the top here of the image viewer. Currently it's set to linear. This will show us the linear data, and if we have a stretch applied, that linear data is visible to us. If we now select the L-calibrated, what this will do is it'll apply the assigned calibration frames to this light frame. And we can see how well the calibration has worked in this individual light frame. It's a good idea to go through an example of each filter and check that everything looks well calibrated before moving forward. If something doesn't look right, then it's worth looking at the master calibration frames. Maybe you assigned the wrong flats or the wrong darks, or maybe it's time to take new flats. But you can see here in this example, it looks pretty well calibrated. The vignetting's all gone. There's still, if we stretch this out, you can still see that there's a light gradient, but that's fine. That's not what we're trying to calibrate out. That's something that we'll remove later with the remove light pollution tool. So I'm happy enough with the blue. I'm going to have a look at the other frames now, but I'll fast forward and do the same process for each. Here's the green data. That looks quite nice, well calibrated. Here's our HA data. Again, that looks well calibrated. Here's our luminance data. Again, looks well calibrated. And finally, our red data. Let's move on to the next step, which is analyze stars. This process will analyze the stars in our light frames, and as part of that, we'll start to see the number of stars, the full width half max, and an initial quality score start to get filled out for each of our light frames in the frame list. After this is complete, I'll do a first pass at removing light frames that I don't want to include in the final integration. There's really nothing to change here. The default 500 seems to work great. If you're doing mosaics, you may want to bump that number up. So we just hit Analyze Stars and wait till that's finished. So that's finished. And we can now see that the number of stars, the full width half max, and an initial quality score are now populated for each of our light frames. The quality score will change as we progress, but it's a good rough indication of the quality of a light frame, just looking at the star size and its shape/eccentricity. If we now sort by quality by clicking on one of the light frames, we right click, we can go down and we can sort by quality. We can then chart out the quality across all our light frames by right clicking on a light frame and go down to create analytical graph and select quality. This gives us a bird's eye view of the relative quality of all of our light frames. What we want at this stage, assuming that we're swimming in good data, is to prune out any obvious outliers. I think looking at this HA data here, there's an obvious outlier here, and maybe some of these steep tails that we have at the end of the various filters. If we work through the blue filter, I can demonstrate what I typically do at this point, and then I'll fast forward through the other frames so as to keep this video at a reasonable length. So if we go to the worst blue frame and double click on it, and load that up. Then in our drop down up here, we can go to star map. So we select that. This will then do a star analysis on this particular image, and we can see the PSF and whether the star is round or elongated. And we also see our min and max, full width half max. So in this example, we can see that our star is quite elongated. We can go back and we can have a look at the calibrated data just to check. So if we have a look at our calibrated data, we can see that yes, indeed, these stars do look a little bit elongated. So to remove this light frame, go all the way to the left, we can deselect it. And then what I'll do is I'll go and look at the next worst blue frame. These look a little bit better. Let's go into our star map and check. So still a little bit elongated. I might remove that frame as well and go to the next worst. This is looking a little bit better. I think that should be fine, certainly at this stage. We might just have a quick look at the calibrated just to check. And this looks reasonably, I think at this stage it's fine. We'll leave it in. I'll do another round of pruning once we've finished the normalization. So now I'm going to go through all the other channels, but I'll fast forward. So I've gone through the rest of the filters. So now we can move along to the registration tab. Registration is where we take a reference frame and we register all other frames against it. So that all the stars line up on top of each other. By default, the application will assign a reference frame for us, but we can change this by clicking on the set reference. Instead, we're going to take whatever the application decides is the best reference frame. If we scroll over to the quality score, you can see there's an integrate for any of the light frames that we're going to include in our integration, and we'll see that that's turned off then for the light frames that we've deselected. If we scroll down, there'll be an REF beside one of these, and here we are. So the best quality luminance is the reference frame. All of the other light frames are going to be referenced against it. For the pattern recognition descriptors, I've never had to change anything in here, but under dynamic distortion correction, I typically change some of the values from the defaults depending on my data. If I'm integrating data from different telescopes and or different cameras, then I'll enable use dynamic distortion correction. Ditto, if this is the case, I'll also disable same camera and optics. You can leave the registration mode as normal unless you're doing mosaics. We can now click on Start Registration. When that's finished, it will populate the registration root mean square column for each of our light frames. This will also update the quality score. If the root mean square is high, so let's say higher than 0.25, you should enable dynamic distortion correction and disable same camera and optics, regardless of whether you are imaging with a different telescope or camera. So if we click on Start Registration, and we'll come back when that's finished. Okay, so that's finished, and we can see that the registration root mean square is now populated and that the quality score is now updated. We'll just check the root mean square values to make sure there's no outliers. Blue looks good, green looks good, as does HA, luminance, and red. So no outliers, I think we're pretty good there. So now we can move along to normalization. So normalization takes care of scaling the data prior to integration. This will take care of integrating data taken with different exposures, different cameras or telescopes with different focal lengths, data taken over multiple nights with different amounts of moon glow, etc., etc. The defaults typically work great, but if you're integrating data taken with different fields of view or mosaics, for example, then you should change the mode from regular to advanced. In this case, we're reasonably close in terms of fields of view, so I'm going to leave it at regular. I've never had to change method or scale. So then we can just go and we can normalize the lights and wait till that's finished. When normalization is complete, then we'll have filled in the background and dispersion and the signal noise ratio and noise in our frame list for each of our light frames. We'll also have a final quality score before moving on to integration. At this stage, I'll rechart out the quality to make sure there are no outliers that I'd like to exclude. I'll do this again for the blue filter and then fast forward for the rest of the filters. So normalization has complete. We can see now that the rest of the remaining columns have been filled out. We have a background and dispersion. We also have a signal to noise ratio and noise. And our quality score is now updated, and this is the final update before we do our integration. If we do another chart, so we right click on one of our light frames, go down to create analytical graph, and we'll chart by quality. And again, we're looking for any outliers here. I think everything's looking good, and we can move along to the integration tab. So now we're ready to do the final integration. This is where we take all our normalized, aligned, and calibrated light frames and stack them. There are a couple of settings here that I typically change depending on my data. If I want to create a synthetic luminance because I have RGB data with no separate luminance, then I select Integrate per channel at all. What this will do is do a full integration across all channels, not just integrate the results of the separate channels. Most of the time, this will generate a decent luminance with better signal to noise ratio than just combining the separate RGB channels and post-processing. It doesn't replace a good luminance, it's just better than no luminance. In this case, I have a luminance, so I'm just going to select Integrate per channel. We want to keep the multi-session option as Integrate all. We want to set our lights to stack to be 100%, as we've manually removed any light frames that we don't want to include in the final integration. We leave everything else here as default, but under local normalization correction, if I'm combining data for a channel for multiple nights, I'll enable local normalization correction. Typically, I'd set this to 2nd degree, LNC, and 3 iterations. As all my channels were taken on the same night, I'm going to turn this off. If I'm integrating with different field of views or telescopes, then I'll enable multiband blending and leave it at the default 5%. If you're doing mosaics, then you bump this up appropriately, and this will help blend any seams in our final integration. Scrolling down to the bottom, I leave all these as default. I sometimes drizzle, but we'll leave that for another day. So I think for now, we're ready to do a full integration. We hit the integration button and we wait, and we'll come back at the end when this is all finished. So the integration has now complete. This is our blue data, our green data, our HA, luminance, and our red data. So that's it. I hope you enjoyed the video. There's a lot to go through there. In a subsequent video, we'll look at processing all of this data in PixInsight and producing a full HA LRGB image of M33.